Uh, so just for you guys who may not know me, my background is actually in physics. So my bachelor and master is like in a statistical physics, and then I moved to Aalto University, and now I'm working on complex networks. So I'm at the computer science department, which is the source of a lot of good and bad things, which I finally talk about, because when you move from one department to another department, there are a lot of cultural things. But today I will talk about like one of our recent work on vaccination. So typically the idea that you may all have heard thanks to COVID is like that if we can vaccinate enough number of people, then everyone would be safe. But the question is like, how many people then should we vaccinate? And from the media, we always hear that like 70% of people should be vaccinated so that we reach something which is called herd immunity. So that if we reach herd immunity, it doesn't matter if somebody is not vaccinated, the entire population would be safe. So this question is like somehow a trivial question to ask, and like from old literature, we can find it that people that have tried to answer and find some sort of like limit for this herd immunity threshold. So if you look at the literature from these very old traditional model, you can basically say that, yeah, if we have some SIR process that people are healthy, then they get sick and finally they get recovered or they die, with simple assumption that everyone can have some sort of interaction with anyone else, then you can see that the threshold would be 1 minus 1 over R naught, which R naught is like the basic reproduction number. So like if for a disease R naught is around 3, which means like on an average, at the earliest stage of epidemic, some guy can infect 3 other people, then herd immunity threshold would be 1 minus 1 over 3, which is like around 2/3, which you round it up, it would be 70%. And that's like the source of all of these advertisements around the world. And like almost all the countries have set their policy according to this formula. So basically, I'm also part of this project, Nordic COVID Mass, so which is part of these Nordic country sort of academic endeavor, so that we do modeling and we look at data and tell government what's good to do and what not to do in the case of current pandemic and other ones. So like even in Finland, the idea was like that if we vaccinate 80% of a population, we would reach herd immunity. But you know, this is like something that you can easily understand it's not true and it's not possible, because a lot of countries have vaccinated more than that amount, even for other diseases, not only COVID, which is like so complicated, but even before COVID, there are cases that people have been above this threshold, but herd immunity was not reached. So we start thinking that let's have a very simple mathematical model that add a layer of complexity over than this heterogeneous, over than this homogeneous mixing. So we were thinking, okay, when people are taking vaccines, first of all, it is not that everyone is in contact with everyone. There is some network structure, and this structure may give us some clue about how this epidemic threshold would be changed. And the first thing that we were thinking that may highly changes the course of epidemic is like that there have been reports that people who take the vaccines are more probable to be connected to each other than those who do not take the vaccines, because this is like a sort of behavior thing.
Yeah.
So like we have 2 groups of people. Those who take the vaccines, they have more dense connection inside them, and people who do not take the vaccine are more connected to each other. And that's the thing. So we always like model these sort of things in terms of biases between these 2 node attributes in a network, right? So our idea was like that if we just add homophily in a network structure, how would herd immunity threshold would be changed? So basically it can be formalized or like model in terms of a stochastic block model or a modular network, better to say, so that we fix the percentage of people who are taking the vaccine, pi v. H is the homophily level in a network, which I described how we have put it in the model, and the degree distribution. So if we fix these 3 things, and we want the network to be otherwise randomly maximized, then we can have some sort of network, and we can monitor the connectivity and like the effective connectivity of network according to the second moment and the first moment of the degree distribution. So basically, the basic reproduction number can be written in this format, right? So given such a network, we have a homophily index, and it is basically written in terms of the fraction of people who are vaccinated, like pi v, or people who are not vaccinated, like pi u. And then pi vv and pi uu is like the probability between two vaccinated people to be connected. So this is like a sort of good function out of pi vv and pi v. So it gives you a good range from 0 to 1 or -1 to 1 about homophily. So when H is 0, it means there is no homophily, and it's just like random mixing of vaccination. And then when it is 1, it's like it's highly polarized, and there are like one major group are vaccinated and one are unvaccinated, and they're not connected. But basically, because these are probabilities, there should be some bonds. We cannot have like every value of them. But anyway, it would be like a good proxy for monitoring a homophily. It has been there in the literature from social networks. So now the question is like that, okay, I'm a network scientist. There are two things that I'm really interested to see. First of all, given such network structures and some percentage of people on the network who are vaccinated, what would be the epidemic size? Or for example, if I have the network, what would be the giant component size for that? Given that now I know that in the giant component of that network, there are two types of people who are vaccinated and unvaccinated. And I can even think about that, okay, vaccine can be imperfect, so they may not work perfectly. So at the end of the day, both type of people can be safe, even if they're vaccinated. And there are two ways that you can basically put it in your model. Well, you can start thinking about vaccine, that they are effective in a sense that if you take the vaccine, after that, when you're exposed to a disease, you won't get it. So with probability f of s, you are safe when some virus is introduced to you, but it doesn't guarantee that you can also stop the transmission of that disease. So basically, there are two probabilities. One, which is about your personal status, and one is about how you can transmit it to other people. So the first one is called susceptibility, and the second one is like that infectiousness. So these are two different things. So for example, for COVID, it is like that most of vaccines are much better in terms of like making you safe, but not that much good in like stopping the transmission disease. These are like two main parameters that you can control it. And if you can think about it, it's like, it's a very good way, because if you're looking at the branching process, you can simply model this thing. So one thing would be the size of the epidemic, because after that, I can use it as a proxy to find what would be the herd immunity threshold. So basically, you can do some branching process and find that thing. So now let's just start with the case that vaccines are perfectly good. And then you will see, I am just sacrificing the mass, but it's easy for all of you to look at it at the paper. So you will see that previously the formula was like what it is in the parentheses at the right. So if the basic reproduction number is given in the fully mixed population, you know the herd immunity threshold. But now when you introduce this homophily, even when vaccines are working perfectly, there would be a dramatic change, and that the ordinary threshold is scaled with this 1 over 1 minus h. So when h is 0, well, you recover the old formula, but when you have some value for that, it means that it is changed. But what is more important is like that for some values of R0, you may come to some real problems. So on the y-axis, you're looking at the critical coverage of vaccine, so how much vaccine is needed to reach herd immunity. And on the x-axis, you have homophily level, and you're seeing it for different like reproduction numbers. So the larger R0 means like the disease is more transmissible. So if you see, for example, so if you see like, if R0 is like 2, which is like this, at some point, you need everyone to be vaccinated, which means that there is a critical limit over this formula, which tells you that if H is at some value and above it, there is no herd immunity to reach. So basically, this formula is giving you some sort of upper bound for herd immunity level. So like the more transmissive the disease is, well, you come to this. So it means that, for example, if you are here, or like one of these points here, it doesn't matter how many people you are vaccinating. There would be an outbreak in the unvaccinated population. It is guaranteed. Other thing would be like, okay, like finding this type of threshold is somehow straightforward, and it doesn't that much depend on the degree distribution because we're following a sort of branching process. So it's mostly based on this assumption that you have a tree-like network structure. But what about the size of the epidemic? Well, you already have seen these techniques that you can use generating functions and like start looking from one node going to another node and see if it leads to the giant component or not. So again, you can define these two different probabilities that if you follow a link, come to a vaccinated or unvaccinated, and write all these calculations and do the math. And you can finally see that the size of people who are vaccinated and unvaccinated can be given through this technique, right? So what would the result be? What would the interesting thing? So now again, on the x-axis, this is homophily. On the y-axis, this is the percentage of people who are vaccinated, and the color is showing you the size of the epidemic. So first of all, these are for two different cases. For the one that basic reproduction is like 1.5, and at the right, it is like 3. So, but when you just start looking at some special value, like if half of a society is vaccinated, and we start going from left to right, so more people are like, come to this into this homophilic status. So first of all, you can see it is like a phase transition problem. Before this red line, the size of the epidemic is 0. And after that, there is something, and it grows monotonically with homophily. So basically, the larger homophily is, the larger size of the epidemic would be. And for like larger values of R naught, it gets worse. And of course, it depends on like the degree distribution, but you cannot simply change the degree distribution and changing the generating function and have almost the same thing. Because this is like for an Erdős-Rényi network structure, right? With homophily. So this is like a Poisson degree distribution. To make it more realistic, you can simply try negative binomial distributions, because with that type of model, you can have some average degree and play with the fluctuations around that degree, because Poisson degree is just like a one parameter thing, right? But the point is like that these monotonic behavior can be changed if vaccines are not perfect. So for example, here at figure E, you can see that if vaccines, if F of S is like 70%, it means like that with 70% you will be safe, then these monotonic behavior is changed. So when you go from left to right, these curves go up and they come down. And it almost should make sense, because if vaccines are perfect, then everything which is happening inside the unvaccinated society, right? But if vaccines are not good enough and you have high amount of homophily, so the point is like that it seems that people are somehow separated. But the point is like, since vaccines are not good enough, even in the unvaccinated population, there are a lot of transmission routes which are not possible. So diseases can go and like make the size of epidemic change. And so for example, for this case, you can see, so this is like the total number of people who are sick. This is the size of the epidemic, which is like going and growing up to some maximum and then comes down. But this is like the number of people who are unvaccinated. So it makes sense. The more homophilic, these people who are unvaccinated, more of them get sick. But for vaccinated people, you see that there is like this concave behavior. And of course, there is some spatial maximum that you can follow. And that maximum depends on the percentage that that vaccine is good enough and how transmissive is that disease. So for example, if your disease is like more transmissible, so for example, this dark blue, you will see that the disease would take advantage for lower values of homophily. But if it is not like that severe, so for example, now most of these Omicron variant for COVID, they are highly transmissive, so R naught is large. So even with little level of homophily, they would lead to large level of epidemic size. But for like previous variant, which were not that much transmissive, we can see that like they will take advantage of like higher homophily in a society. So like if there is a disease which is not that infectious, so it needs a high amount of homophily in people in terms of vaccine adoption to just grow. So another thing is like that this H, which is like a very special thing that gives you the maximum epidemic size, when vaccines are working perfectly, they just depend on R0 and vaccine efficacy. So there is no dependence on the number of people who are vaccinated, and that's a thing, because this dependence of number of people who are vaccinated is like giving a good clue of how to, for example, advertise for vaccine in a society. Because like if you're a government and you want to decide how many people and in what way they should get the vaccine, it matters. Yep, that was like a very short thing over our paper. But the point is like that if you follow this thing that we have done, it can be easily shown that this is not just not about vaccines as like a sort of intervention. You can basically use this technology of, this machinery to model all type of interventions that you would like to. So for example, what happens if people wear masks? What happens when people do social distancing? And what happens if there are some health behavior among them? So for example, for the case of contact tracing, which all of you may have heard or used this type of apps in, so the idea was like that you install some mobile app and they're supposed to communicate with each other through Bluetooth signals. So like if you are in a shopping center next to some guy who is using the same application, then this contact would be saved. And in future, if you get tested positive, that guy would receive an exposure notification and would quarantine himself, and it would reduce the number of secondary infection to a good amount. So basically, digital contact tracing would really help the course of the epidemic. We have also done a paper on this, and we have shown that with almost the same techniques. So you can see both of our works. The top one is like the vaccination paper, and the bottom one is like this epidemic spreading with contact tracing. And in that work, we have shown that digital contact tracing can be a great tool, especially it's cheap. So if we can implement it in a society, it would reduce the number of secondary infections to a large amount. There are some conditions and criteria. For example, contact network is a case of concern in these sorts of things, and other, of course, privacy issues. But basically, this is like one of the best things that we have, because the point is like that solving an epidemic, it's not rocket science. It is much more harder, and it is much more difficult. And the vaccines are not the only thing that we can curb the pandemic with that. We need vaccines, we need contact tracing, we need masks. So we need all of these things combined together. And each of them have different like influences. So we should monitor how these can help us. And like as a government, because if you want to use some sort of like intervention, you should always look at its costs, right? So vaccination is a typical and traditional way of that, but like contact tracing is like, especially this digital thing, is a new thing that we have at the current time. So I would like to stop here. If there is any question, we can go through them, and then we can go for the next part of the talk, which is about difficulties of doing research.
Thank you, Abbas. I have a question related to the very start of your topic. So when you say the herd immunity is reached, is there any quantitative definition of what do you mean by herd immunity is reached?
Right. So basically, the idea is like that you start doing vaccination, right?
Mm-hmm.
And the idea is that when somebody is vaccinated, that guy is removed from the network. So it is a sort of side percolation. Okay. And when somebody is removed, the size of joint component changes up to some point. So it is like that you are doing this vaccination percentage, and you look at the size of the joint component of that graph. So if I mean, it should be something like that. For if few people have like up to some spatial point, the size of giant component is something like that, then it drops. So this is like the critical percentage of vaccination that you need so that the size of giant component gets below it. And if you just look at this formula in a way that like, you can see that, okay, pi v is the percentage of people who should be vaccinated. So 1 pi v is people who are unvaccinated, right?
Yeah.
So put it here and then put that here. So this quantity is basically the effective reproduction number. So
okay.
This is like a sort of thing that how your exponential growth can be in a tree-like thing. So you can always look at this and use it as a sort of monitor. So, okay, if this is below 1, there would not be a huge transmission.
Okay. Yes, I see. Thank you.
Yeah.
Thank you. Any other questions from the audience? You can simply unmute yourself and ask your question.
I've lost the definition of the parameter age that should be the homophily one.
Yeah, so basically in a network like this,
yes,
you have this part of society. So pi v fraction of people are vaccinated, right? Then this link between two vaccinated people, between 2v is pi vv, and these are unvaccinated people, so this is pi uu. And then these links from this part of society to that part of society is given with like pi uv or pi yu, pi vu. So basically, you can control the amount of homophily with pi uu or pi vv because it's saying that people of the same status are connected to each other. But there is a technical problem. The problem is like that when you change pi v, then it is not giving you a good measure. In a better sense, if you just want to have a good proxy for homophily here, we want something one-dimensional and a good thing. So basically pi vv and pi uu are, pi v and pi vv are not perpendicular to each other. So you cannot use it as a good type of proxy. So if you just then define this thing in this way, then it would be fine, because first of all, it doesn't matter if you write it in terms of vaccinated or unvaccinated, it's completely symmetric. Then it is like a monotonic function of that. So like this is the probability between two vaccinated people. So the larger it gets, the larger homophily gets. So it's a good thing. It is an increasing function of this, or like pi uu. On the other hand, you can see that the value simply changes between -1 and 1. And you can see like if everyone in a society is like, so let's say that everyone is connected to, or let's say there is no vaccinated people. So pi v is 0. So then the entire thing is like given by this part of the formula, which completely makes sense. But then you start increasing these vaccinated people, then you can see that basically changing these probabilities would change age differently. That's the reason that people in like social network analysis use this type of index for monitoring homophily in a network.
Okay, thank you.
Yeah.